Yes, hello guys. Welcome back to part two of the teaching machine. Part one is done. The model learned from those 266 penguins got tested on 67. It had never seen and scored 99% accuracy. That is supervised learning, learning with a teacher with answers given. Now we flip the script completely. Part two is unsupervised learning. We are going to take those same 33 penguins and hide all the species label. The computer gets the measurement only. No Adele the singer, no Gento the drummer, no chain strap the rapper. Just numbers. The question is, can the computer figure out that there are three distinct groups all on its own? Yeah, let's get started. Before we go on, uh, let us understand what K-mean means. K-mean means, yeah. So we find the group. And so let's think of it like this. Imagine you find a huge box of Legos. You know Legos, right? The Lego tiles, and then it is put on the floor. Nobody tells you the categories, no instructions, no pictures. You just start by sorting out the similarities by the patterns that you are seeing. You might just put all the flat pieces in one pile, the long ones in another pile, the small round ones in a third. That is exactly what k-means does with data. So here is how the algorithm works. So think of it like K is the number of groups that you want, and K means the center point, the average in the data. Then every every penguins get assigned to his nearest center, like the nearest center. Then the centers now start moving to the middle, small, around their group. Then the penguins is assigned to the nearest center again, and this repeats until nothing changes. So, but one important catch here is that our body mass is in the thousands of grams and bill length is around 40 millimeter. So if we don't scale it, the mass would bully everybody. The mass is like the big kid in class that has huge body and the mass is basically a bully in our data set. So what we need to do is that we need to scale it. So we scale everything first, and once we scale everything first, then and here is the experiment. Like, we know that there are three species the computer does not know. So will it discover on its own just from measurement? I guess we'll find out. So let's go to our Google Colab again. Yes, this is our Google Colab again. So part two, unsupervised. I explained import pandas in part one, import seaborn, import matplotlib. You can see that from the supervised learnings, three things has changed. That is, we are using skill learn preprocessing, which is the standard scaler. Just like I mentioned earlier, that we need to scale, and then the model we are importing is k-means. This is our importation of modeling, and then we can see here the silhouette score. That is how we judge how good our clusters are. We'll come to that. So let's run cell one and print our tools. Then let's pick cell two. We did something different here. um in our data set here, we dropped the missing column directly because we already dropped it in the previous one, but we are dropping it directly with drop NA, that is drop empty measurement. You can see the user guide, missing data for more values considered missing. So, and then the x equals to penguin features, we are dropping the features we are keeping it a secret until the end. So we run cell 2 and then we see x dot head. We can see that the missing features, the species has been hidden. We only have the build length, build depth, flipper length, and body mass. So we can notice that as the computer has no idea now that there are three categories of species, but our job now is to identify if the computer can locate these things. So let's go back to our cells and copy cell and copy cell 3. Yes, standard scalar. We'll copy cell 3 and cell 4 together. Let's copy cell 4 too. But we run cell 3 first. Okay, so we can see that the standard scalar, it transforms all our measurements. So each one has an average of 0 and a spread of 1. Like, so it means that it will now go from 0 to 1, 0 to 1, 0 to 1, 0 to 1. After this, the build length and body mass are on exact equal footings. They are now all balanced. No single measurement can dominate based on its units. So let's run cell 3, fair comparison ready, and then cell 4. This cell 4, this is called the Hebo method. Why is it the Hebo method? This is how we will decide how many groups to use. We try k equals to 1, to k equals to 2, to k equals to, we can see here for k in range 1 to 9. So that is, we try k equals to 1 all the way to 8. For each value of k, um we run and record the inertia. So the inertia is like a scores that measures how tightly packed the group are. So lower inertia means that tighter groups and higher inertia means the otherwise. I'm sure some of us are physics students. Inertia is like an external force that keeps a body in a state of rest unless compared otherwise. If I'm not right, you can fact check that and correct me. I'm open to learn. Then we plot those scores on a line graph. A graph will appear, the line will drop steeply at first, then flatten out. Somewhere in that graph, there is a bending point, just like an elbow. You know, when people relax their elbows, there is like a bending point. When they straighten it, it is straight, it is flattened down. But when they relax it, there are different degrees to an elbow. You can see 45, there's 60 degrees, there's 90, like in that context. So we will come back to the bend is the elbow. The bend is the elbow. See, look for the bend. The bend there is the elbow. The bend is the elbow. We'll come back to this slide and we'll look at how to read it properly. So yes, the elbow method. Yeah, so just like I was explaining, the inertia is the messiness score. How far the penguins sit from the center of their pile, lower equals to tighter piles. The group always loves it. The catch, more group loves it. With 33 piles of one penguins each, inertia is 0 and useless. So it never asks like where is the best score coming from. So but here is the trick. If you keep adding more groups, inertia will keep going down. You keep going down. Inertia always goes down. With like let's say 33 groups, one penguin per group. So we'll have like the inertia would always be 0, but that is useless. So we never ask it where is the lowest score. Like we ask it smarter question, like where does the improvement stop being dramatic? That's exactly what the want to what the that where is the next point of improvement? That is exactly where point 2 to 3 drops, and then um that is exactly where the point drops. I'm trying not to dwell too much on this because of the time. So we use the same we the honest take about this is that the elbows are not always sharp and obvious. We just need to like understand that sometimes they are gentle bend. If your graph has no clear if your graph has no clear bend, that is a finding too. It means the data does not have like obvious natural groupings. You say so, you do not make one up. Do you understand? You specify. Always talk about your data limitations. Don't assume. Don't 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 assume. Always specify. Like you chin up and man up and understand that, oh, the data is limited or something. So yes, your turn is the question I want to ask you is let's go back to our slide. What is scale? Like in your cell that you run, what is scale? Say your answer out loud before moving on and say why. And then when you say why, you fact check with this next slide. So what is k? Well, k is equals to 4, and here is why. Let's go back to our elbow. Here is why. Look at the step from 1 to 2. We can see that the inertia drops by 850, and then from 3 to 4 it drops like by, let's say, like from 2 to 3 it drops like 450, and then from 3 to 4 we can see that it drops like by 320 thereabout, and then it keeps dropping. But look at the flat forehand from 4 to 5. We can see that the drop is only about 45. From 5 to 6 there's like less drop too. So adding more groups has basically stopped helping. The machine has stopped helping. So they are just sitting in piles that are together already. So k is 4 because this is the last point where adding a group made a difference. K is this point where it stopped adding a difference. So if you set 3, you can look again at that drop from 3 to 4. You can see that it's nearly half of what is left. Do you understand? So that is too big to ignore. But this to this, there is not much difference. So the big lesson here is the penguins had 3 groups. This data has 4. The number always comes from the graph, never from the habit. So every data set gets its own elbow plot and its own answer. Never do what? Never assume. So moving on, moving on to our next slide. Let's let's cluster and see what gives. Let's copy cell 6 to let's copy cell 6 to yes. Let's see what gives. So this is the cell 5s. The fit dot predict. Yes, this is us importing the model k-means, and then the fit dot predict does two things at once. It trains the model and immediately assigns every penguins to a group, that is 0, 1, and 2. 0, 1, and 2. You know what 0, 1, and 2 means at the back of your mind because we did supervised learning just now. So we run it and look at it. So see, the 0 has 129, 1 has 119, 2 has 85. So that's it. That's the 3 groups. And then the cell 6 should show us a scatter plot. Let's see what gives. Yes. So the cell 6 shows us a scatter plot. You can see that the computer has the model has found structure in the data without using anything but numbers. We'll come back to this slide and we'll read it together. So we'll come back to this scatter plot. Let's go back to our slide. See, this is the scatter plot, and now to read it. So each dot is one penguin, purple, yellow, and teal. Am I right with the colors? Yeah, purple, yellow, and teal. We can see that every dot is one penguin. Its position is set by two measurements: the flipper length and then the bill length. The color is the group numbers the computer give it. The color is the group numbers. Remember, the computer grouped it into 0, 1, and 2. So, like the review, the small all-rounders would probably reveal that these are the Adele's, the singer, and then the yellow cluster, which the bills are much bigger. This would probably be like uh the chain strap, this ones, and then the teal, which is on this far right. Yeah, the teal, we can see that these are mostly the chain strap, the wrappers, because they have long filters, long flippers all the way across. These are the big ones. And Gento, these ones are the chain wrappers, sorry. And then these are probably the gentos, because they are the largest of the three species. So if we notice where the color overlap, we can see that there are boundaries. Some penguins sit right between the two clusters. These are exactly the mixed up that the see you can see here, you can see some here. So these are exactly the mixed up that the data is having, that the model is having. There are some clean separations in some places. Like there's some clean separations here. Just draw an imaginary line here. There are clean separations here too. So, like, these are the honest overlap, and this is what the data actually looks like. This is what data actually looks like in the real world. So let's copy the next cell, which is the last cell. Let's see the scores. Let's see what we have. So the silhouette score is 0.45. Closer to 1 is tighter, clearer groups. So the computer discovered the three species. We can see that a score near 0 means that the groups are blurry. But our penguins usually land around 0.45, which shows that which is actually really decent, and which is actually really good. The second part is the real review, which we can see the PD dots cross tab. It shows us the computer's group versus the real species. So we can see that the Gento almost separates well. The Gento separates almost perfectly. It's even perfect sef. The Gento is really perfect. We can see that the chain strap and the Adele, they have some overlaps. It's also the same in the supervised learning. We could see that there was a mixed up within the chain straps and the Adele. So you can take a time to think about what happened here. The computer had no idea there were three species. It only had four numbers per bed, and it got mostly right. So that is the power of supervised learning. So let's quickly talk about the the evaluation metrics in unsupervised learning. Yeah, the evaluation metrics in unsupervised learning. So this is trickier than supervised in a bit, because there is no answer sheet. We have to like judge it on our own. So we have three tools: the initial and elbow, and the silhouette score, and the review table. The initial and elbow, it measures how tightly packed each cluster is. We plot it for different values of k and look for the elbow where adding more groups makes it completely meaningless. Like where adding more groups in the sense that where the model has stopped learning. And then the silhouette score is for each data point is like thinking that am I close to my own group or far from others? Like you are going on an hiking journey and then you are thinking, are you far from the group that you went with, or you are far from others? Are you close to your group or you are away from your others? Imagine not being close to your group. You will feel left alone. That's where we see the overlap in the data. But when you are close to your group, so it's like close to your group means close to your group. So the score runs from -1 to 1, like I mentioned here. Near one is like is when is close. It means that is close to one means that it is well represented, and close to zero means that there are blurry boundaries, and our penguin scores land around 0.45, which is good. And then the review table, we cheated and check, and today the review table is like we fact check what exactly it is that the model has done. Yes, so we compared with what we kept earlier, and the cross tab let us to see like where the computer matches the real species. The Gento was separated brilliantly, but the overlap was the Adele and the chin strap. So you can ask yourself this question, that what is it about their measurement that makes them harder to separate? In a real unsupervised project, you would not have those true labels to check against. You would rely only on the inertia and the silhouette score. The review is a bonus because we set it up deliberately today, but in real world settings, it might not be so. So here are some data sets that you can explore, and you can try and find out. The Titanic is actually really common. You can explore this data set to see what's going on. You can do it for supervised and non-supervised. For the Titanic, you can do it like the supervised predict who survived and who did not, and then you can have a conversation about it. And then the digit is like 1797 handwriting numbers, and then you try clustering them and see what gives. So you can load any of the data sets in one line and try it out. So yeah, that is day two complete. That's day two recap complete. So let us recap what we can talk about confidently now. Supervised learning is learning with answers. We train on 80%, we test on the unseen 20, we judged today with an accuracy and a confusion matrix. And then unsupervised is like finding structure without any answers at all. We scale first, we pick the K with the elbow, we run the K means, we judge with the silhouette score. And the thing that should stick with you is that the computer took 4 body measurements from 33 penguins. Nobody told it that there were 3 species, and it mostly found them anyway. That is what makes machine learning powerful. That is what makes machine learning what powerful. And it finds patterns that would probably have taken me a whole day or weeks to spot normally. So yes, stay tuned for day 3. We'll be working on an end-to-end project and we'll see what gives. Today is the foundation, and day 2 is over, and we look forward to seeing you on day 3. Thank you.